Let's move to plane design. Plane design starts with foil analysis, so we go back to the X-foil direct analysis view. And why does it start with foil analysis? It's because a wing is made of foil, of course, but more important than that, we lack a proper viscous model for 3D analysis. We do have one in 2D, and that's what is provided by X-foil, but we have no real way to calculate the viscous drag in 3D. There's no simple theory for that. There may be complex theory, but it's just too complicated for programs such as XFNR5. So what we do, because we want to calculate our model aircraft at low speeds, the viscous properties cannot be neglected. They are of the same order of magnitude as the induced drag, which is another effect, another kind of drag. And if we don't take into account viscous drag, we'll be missing a good part of the viscous properties, and we'll be overestimating the performance of our planes. So how do we do that? We don't have a viscous theory for 3D, but we can't make without either. So what we do is we try to evaluate it using 2D analysis, using X-foil analysis, and then we'll try to use this data and add it sort of to our 3D results. And this is why we need to look at 2D analysis of all our foils and try to evaluate the viscous drag for every Reynolds number and angle of attack that will be seen by each foil of each wing of each plane we're going to calculate. Well, sounds a bit vast, but it's not that difficult. The way we do it, we run a batch analysis of all our foils. And since I'm going to use all these foils later on, I select them all and we'll calculate them from a range of Reynolds number from 20,000 to 1 million, and this should cover all the Reynolds number that we will need later on. And we will calculate these foils, let's say, for a range of -7 degrees to 10 degrees with an increment of 0.5, starting always from 0. And I will leave unchanged the transition parameters. Okay, let's analyze this and check our display here. Okay, analysis completed. We can close this window. And we can see that we have created what I call the polar mesh for each of the foils we are going to use. Let's check one of them. For instance, the AG25 modified, which we created just before, and display only these polars. Well, they have a nice shape, which means the analysis runs smoothly. And they cover a range of AOAs from -7 to 10. Okay, looks good. Maybe when we run the analysis, the plane analysis, we'll find that some foils, for instance, operate in this range here or this range here, and are not between two polars. And the analysis will fail then because it can't deduce from these curves what the drag, for instance, or the lift is in this area here. If that's the case, we'll see it in the analysis log, and we'll have to come back to this module to complete the polar mesh. But right now, let's leave it as it is, and we can save the project just to make sure and switch to plane design.